Ever wondered how AI can detect a tumor in a medical scan faster than a human radiologist? The answer lies in medical image segmentation, a process where algorithms learn to precisely outline anatomical structures in images like CT scans or MRIs. But traditional models, they're like detectives with tunnel vision, often missing contextual clues or getting lost in noise. Enter TCSAFormer, a revolutionary architecture that's redefining accuracy and efficiency in medical imaging. Let's dive into the science behind it. Imagine analyzing a CT scan of the lungs. A standard AI might struggle with blurry edges or misinterpret shadows as actual tissue. TCSAFormer tackles this by combining two key innovations: token compression and sparse attention. Token compression works by distilling raw pixel data into meaningful tokens. Think of it as pruning a tree to focus on its most critical branches. Instead of processing every pixel equally, the model prioritizes regions with high diagnostic value, drastically reducing computational load without sacrificing detail. But here's the breakthrough: sparse attention. Traditional attention mechanisms force models to weigh every part of an image equally, like scanning a room with a floodlight. TCSAFormer, however, uses a targeted approach. Think of it as a flashlight that illuminates only the most relevant areas. This isn't just faster, it's smarter. By focusing on key regions, the model avoids distractions, achieving state-of-the-art accuracy while using 34.7% less computational power than competitors. The second pillar of TCSAFormer is its dual-branch feed-forward network, DBFFN. This architecture splits processing into two specialized pathways, one for high-resolution details, like the jagged edges of a lesion, and another for broader anatomical context, such as organ positioning. It's like having two experts collaborate. One zooms in on microscopic textures, while the other maps the entire landscape. This dual perspective allows the model to not only identify structures, but also understand their relationships, mimicking human-like spatial reasoning. Researchers tested TCSAFormer on benchmark datasets like Synapse, abdominal scans, and ISIC-2018, skin lesions. On Synapse, it achieved an 83.16% dice coefficient, a metric measuring overlap between AI predictions and gold standard annotations, outperforming existing models. On ISIC-2018, it matched top performers while cutting inference time by 40%. These results aren't just numbers, they represent faster, more reliable diagnoses. Why does this matter? Consider a radiologist reviewing a brain MRI. With TCSAFormer, the AI could rapidly segment tumors with sub-millimeter precision, reducing manual corrections. For surgeons, this means pre-op planning with 3D models that highlight critical structures. The implications are profound. AI isn't just automating tasks, it's enhancing clinical decision-making, potentially saving lives through earlier detection and more accurate interventions. TCSAFormer isn't a distant future concept. It's a tangible leap forward in AI-driven healthcare. By marrying efficiency with precision, it sets a new standard for medical image analysis. As researchers refine these techniques, we're not just improving algorithms, we're empowering clinicians with tools that see deeper, act faster, and ultimately heal better. Want to see how TCSAFormer outperforms traditional models? Check the study's visual comparisons. Its segmentation maps are a masterclass in clarity. And if you're curious about how this could transform diagnostics, the answer is simple: it's already happening. Stay tuned for more deep dives into AI's role in medicine. Until next time, keep exploring,